Welcome to a course on complex analysis. In the previous lecture, we have discussed about the singularities and the concept of residues. In this lecture, we will see what is Cauchy residue theorem. Okay, in the previous lecture, I ended discussing about suppose we have many number of singular points inside a domain. Then what happens about the integration? Then what happens with the integration? So this is where I ended the last lecture, and the answer is given by Cauchy residue theorem. Okay, here if you see, just a minute, yeah. So here if you see, you may have a domain of this sort inside which there may be many points at which, okay, there may be finitely many points at which the function has singularities, right? So around each point we find some neighborhood. Okay, so this one let me take it as c1, this one let me take it as c2, this one let me take it as cn. So likewise I'll have to choose n different neighborhoods of the respective singular points. Okay, so this entire thing we take it as c. Now this is the case we are going to deal. Okay, let C be any simply closed contour described in the positive sense. And if a function is analytic inside and on the contour C except for a finite number of singular points, and that we have taken as z1 to zn, right? Then integral over C f of z dz is 2 pi I times of residues of the residue of the function f of z at each of these points, which means first of all you will have to find out the residue at z equals z1 to this function, okay, to this function, and you will have to find out the residue at this point till residue at this point. Finally, okay, we just add it up, we multiply that quantity with 2 pi and that is going to be the integral value. Okay, this is what the Cauchy residue theorem tells us. Okay, now let us start the proof of the theorem. Okay, so to prove this, just a minute. Okay, no issues. The proof of the theorem, let the points z1, z2, zn be centers of positively oriented circles ck, where actually these circles are interior to C. Okay, we will have to identify disks in this way, and they are so small, and they have to be, these circles have to be so small that no two of them have points in common. So which means what, these circles must be non-intersecting circles. We'll have to identify circles of that form, right? Now the circles ck with k running from 1 to n together with the simple closed contour C form the boundary of the region in which f is analytic. That is, we are just looking at the the shaded regions. Okay, we are just looking at the shaded regions. Here you may very well notice that in the shaded region, the function, your function f is analytic everywhere. So this shaded region will have the boundary, that is the circles and the closed contour together gives us the boundary, right? So on which f is analytic and whose interior is a simply connected, sorry, this is not a simply connected domain, this is a multiply connected domain, okay, consisting of the points inside C and exterior to CK. So by Cauchy theorem, we get integral over C f of z dz minus summation k runs from 1 to n integral over ck f of z dz equals 0. This tells us integral over c f of z dz is summation k runs from 1 to n integral over ck f of z dz. About the particular point, suppose integral over ck f of z dz is residue, that is the residue of the function f of z at z equals zk. So we'll have to collect all those residues and make a sum, then you get this. So this completes the proof. Fine. So now let us see an example. So we have integral over c 5z minus 2 upon z multiplied with z minus 1 dz. So this is the thing that we have. And here C is the circle, absolute of z equals 2, which is described in the counterclockwise, that is anti-clockwise. Here this function has two singularities, 0 and 1, which are isolated. Okay, so we'll have to calculate the residue about these 2 points. Okay, we have 5z minus 2 upon z multiplied with z minus 1. So this one, let us write it as a upon z plus b upon z minus 1. So this gives us 5z minus 2 equals a multiplied with z minus 1 plus bz. When z equals 1, then we get 5 minus 2, which is 3 equals b. Okay, so we get the value of b. When z equals 0, we get minus 2 equals minus a, which means a equals 2. Therefore, the function 5z minus 2 upon z multiplied with z minus 1, this may be written as 2 upon z plus 3 upon z minus 1, right? So this is what we are going to have, right? So with which, what can we do? Okay, now it is already in the form of Lorentz series, so we don't have to worry about the first term. Now let us go to the second term. Okay, so this is already in the form of Lorentz series, so we just don't worry about this one. And when we do for this is 3 has to be multiplied with what? Actually minus 3, 1 upon 1 minus z. So this is how we write our yeah. So we shall have this as it is. About what point we are doing? About the point z minus 1. So if it is so, then what should we do? We must have the z minus 1 as it is. Okay, now I think we are now done. Just a minute. Are we very sure about this? Yes, yes, we are done. So if you see, now it is in the form of Lorentz series. Therefore, residue of f of z at z equals 0 is 2. That is coefficient of 1 upon 2. And residue of f of z at z equals 1 is 3. Okay. So from which, what can we say? Integral over c 5z minus 2 upon z multiplied with z minus 1 dz. This is equal to 2 pi I times of the residues. So which is 2 plus 3. So we get 10 pi I. This is the integral value. Right? So this is one way of writing. Now let me tell you the other way. So the other way, let me do it in blue color. Okay. That is the alter method. So here we have 5z minus 2 upon z multiplied with z minus 1. This one we write it as 5 times of z minus 1. Okay, let me write this way. So it becomes what? 5z minus 5. But we have only minus 2. So we'll have to add 3 upon z into z minus 1. Okay, so this quantity. Now let me write only this way, and that z, let me write it as this way. Okay, so this is simply 5 plus 3 upon z minus 1, which is to be multiplied with 1 minus z minus 1 plus z minus 1 squared minus etc. It goes this way. Here your region is 0 smaller than absolute of z minus 1 less than 1. So from this, if you just multiply the things inside, you can very well see that your b1 value is 3. Okay, so it is quite trivial that your that is your b1 here. Your b1 here is residue of the function f of z at z equals 1. In a similar way, you can obtain, that is, first of all, let us have this one as 5z minus 2 upon z, and this one we are writing in a form that minus 1 upon 1 minus z. So which is 5 minus 2 upon z, which is to be multiplied with minus 1 minus z squared minus z cube, and it goes like this. So it is, when you multiply it inside, minus 5 minus 5z minus 5z squared minus 5z cube, and it goes this way. Then plus 2 upon z plus 2, then plus 2z plus etc. So from here, residue of the function at z equals 0 is 2. So from this we identify the value is 2. Even here, integral over c f of z dz is nothing but 2 pi I, and the residue values are 3 and 2. That gives us 10 pi I. Okay, we can use either of this technique to calculate the residue value. Now we move to the concept called residue at infinity. So when we talk about residue at infinity, this is given in a theorem. Let me first state the theorem. If a function f is analytic everywhere in the finite plane, except for a finite number of singular points interior to a positively oriented simple closed contour C, then integral over C f of z dz is equal to 2 pi I residue of z equals 0 1 upon z square f of 1 upon z, this one. So residue of z equals 0 is equivalent to say that residue of uh, when you change that 1 upon z as z, then your residue z equals 0 is your residue z equals infinity. Okay. Now let us see how to proceed with the proof. Suppose that a function f is analytic throughout the finite plane. When we say something as finite plane, here the finite plane refers to the context, that entire complex plane. When you extend it to an extended complex plane, then it is not a finite plane, which means when you include the point infinity to a complex plane, that becomes extended complex plane. Usually the complex plane can also be called as finite plane. Okay, so it is analytic throughout the complex plane except for a finite number of singularities interior to a positively oriented simple closed contour C. Let R1 denote a positive number which is large enough that the contour C lies inside the circle absolute of Z equals R1. If you just see what is the thing that we are trying to construct here. So we are choosing R1 large enough. Okay. So we are constructing R1 large enough such that your R, your contour C is completely lying inside. Just a minute. We shall have this way. Yeah. So we shall have this as our contour. So this is completely lying inside this. This is what? This is how we'll have to choose R1. Okay. The choice of R1 must be in this way. Now the function f of z is analytic throughout the domain R1 smaller than absolute of z smaller than infinity. Okay, and the point at infinity is then said to be a isolated singularity of f. Why is it so? Here, notice that all your singular points are lying inside C, right? So R1 is chosen to be some positive number which is large enough to contain that contour C inside it. So which means your point infinity is outside R1 only. So in the neighborhood of infinity, you will have no points which are singular points to the given function, right? So we cannot identify any point which is a singular point to the given function near infinity. So that is what we are saying. So the point infinity must be an isolated singularity of the function f, right? So after which we proceed with the fact that let C naught denote a circle absolute of z equals r naught oriented in the clockwise direction where your r naught value must be bigger than r1. We'll have to identify such r naught. Okay. So the okay, if we just, so r naught would be somewhere. So this must be the circle C naught with this point R naught. Okay. So therefore the residue of f at infinity is defined as integral over C naught f of z dz, which is 2 pi I times of residue of z equals infinity to the function f of z. Okay. We mark this as equation 1. Now note that the circle C naught keeps the point at infinity on the left since f is analytic. Throughout the closed region bounded by C and C naught. So if you just see the closed region bounded by C and C naught means what? That region, let me shade it in different color. So this is the point C, and this is like this region. Okay, inside this region we do not have any point of singularity. So your function is analytic in this shaded region. So what we say is that by the principle of deformation of paths tells us integral over c f of z dz, which is minus c naught f of z dz. Okay, so c naught is taken in this direction, right? Even if we take it in the positive direction, then okay, so this is, we know that this quantity is equal to this. In order to make use of the principle of deformation paths, we have taken c naught in the opposite direction to that of c. Only then we can make use of this deformation of paths, right? So now by equation 1, integral over c f of z dz which is minus 2 pi I residue of z equals infinity to the function f of z. Okay, we mark this as equation 2. Now the claim is to find the residue. How to achieve it? So we consider the Lorentz series. Consider the Lorentz series. F of z equals summation n runs from minus infinity to infinity Cn z to the power n, where r1 smaller than absolute of z smaller than infinity. So about the point 0 we are talking now. So we have this one, right, where your Cn is 1 upon 2 pi I integral over minus C naught f of z dz upon z to the power n plus 1 with n running from 0 plus or minus 1 plus or minus 2 etc. So we mark this as equation 3 and we mark this as equation 4. Now replace z by 1 upon z in expansion 3 and then multiply by 1 upon z square. We get, so when you replace 1 upon z, you are going to get f upon 1 upon z equals summation n runs from minus infinity to infinity Cn 1 upon z to the power n. So this is what we are going to have, right? So this is summation n runs from minus infinity to infinity 1 upon z to the power n. When you multiply 1 upon z squared with this, so this is 1 upon z squared summation n runs from minus infinity to infinity 1 upon z to the power n, which can be written as etc. till 1 upon z squared plus 1 upon z plus 1 plus z plus z squared plus etc. It goes this way, and this may be written as etc. till when you multiply this 1 upon z to the power 4 plus 1 upon z cube plus 1 upon z squared plus 1 upon z plus 1 plus etc. It comes like this. Okay, even this can be written as summation n runs from infinity minus infinity to infinity. In all the places we have added power 2. So 1 upon z to the power n plus 2. We can write like this. Okay, so we have written till this, and when we wish to change this to something else, that is 1 upon z squared f of 1 upon z is summation n runs from minus infinity to infinity 1 upon z to the power n plus 2. When we change this to the okay, let me have it as m 1 upon z to the power m. This is what I wish to have. Okay, so I take m n plus 2 as m, which means what? Just a minute, am I doing it right? No, I just made a mistake. Here we'll have Cn, right? Cn. So C minus 2, C minus 1, C naught, C1 plus C2. So here C minus 2, C minus 1, C naught, C1, C2. So it is Cn, this one. So when we change this, when n plus 2 equals m, your n is what? M minus 2. So m minus 2 from minus infinity to infinity only. So when we change this, this is summation n runs from minus infinity to infinity. Since m is a dummy variable, we just change this to n. So this is what we have. Okay, this is valid in this region. Here, if you try to find out what is the value of c minus 1, it just what is the value of c minus 1? That is the residue of this quantity, right? So put n equals minus 1 in expression 4. We have c minus 1 equals 1 upon 2 pi I integral over minus c naught f of z dz. So from this we write integral over c naught f of z dz is minus 2 pi I residue at z equals 0 to the function 1 upon z squared f of 1 upon z. Okay, so which means that is by equation 1 we get residue at z equals infinity to the function is minus times of residue of z equals 0 to the function 1 upon z squared f of 1 upon z squared, sorry, 1 upon z. So we have now done, right? So this is integral over c f of z dz is 2 pi I times of residue of z equals 0 1 upon z squared f of 1 upon z. This completes the proof. Okay, now we will see some example. Consider the function f of z equals 5z minus 2 upon z multiplied with z minus 1. We have seen it already in the previous thing. So there we have calculated the Lorentz series expansion and found the residue thing, everything, right? So now let us calculate the residue of this function z equals infinity to f of z. What was that? That is minus residue of z equals 0 1 upon z squared f of 1 upon z, right? So now let us find what is f of 1 upon z, which is 5 times of 1 upon z minus 2 upon 1 upon z multiplied with 1 upon z minus 1. So this is simply 5 minus 2z upon z divided by 1 into 1 minus z upon z. Here also we have z. So 1z and 1z gets cancelled, and when this z goes to the or we may simply have 5 minus 2z 5 minus 2z, if I'm not wrong. Just a minute, let me check my answers. Yeah, so 5 minus 2z upon 1 minus z to be multiplied with z. So this is what we have, isn't it? Okay. Did we leave anything? So now we'll have to just multiply 1 upon z squared with this. So f of 1 upon z, which is 1 upon z squared multiplied with 5 minus 2z multiplied with z upon 1 minus z. So 1z and 1z gets cancelled. So we are left with 5 minus 2z upon z multiplied with 1 upon 1 minus z. Right? Now we will have to expand this. So the first is 5 upon z minus 2 multiplied with 1 upon 1 minus z. So that is uh, 5 upon z minus 2. When we expand this in the Lorentz series, we get 1 plus z squared, etc. It goes this way. So this is 5 upon z plus 3. So when we multiply this with this, we get 5, and here do the calculations. It is quite simple. So this is the thing that we are getting, and this is valid in this region. Okay. So when you do so, from this you can very well decide that residue of z equals 0 to the function 1 upon z squared f of 1 upon z, which is equal to 5, which is the coefficient of 1 upon z. Therefore, your integral over c f of z dz is minus 2 pi I times of, okay, minus 2 pi I times of this quantity. So which is minus 10 pi I. Right? The next ideology that we are going to see is three types of isolated singular points. So this isolated singular points are divided into three categories, namely poles, removable singularities, and essential singularities. These are the three types of isolated singularities. When the singularity is non-isolated, okay, then we don't have to talk much about non-isolated singularities. Once you identify that as a non-isolated singularity, that is completely fine. Okay, so but if it is isolated singular point, then we'll have to examine which type of thing is this. Okay, we know if a function is having a singularity at particular point, then we can expand that in the Lorentz series, right? So the Lorentz series expansion is of this form: summation n runs from 0 to infinity a n z minus z naught to the power n plus b1 upon z minus z naught plus b2 upon z minus z naught whole squared, etc. till bn upon z minus z naught to the power n, and it goes like this. Okay, in the punctured disk, in 0 less than absolute of z minus z naught less than some r2. Okay, so we can have Lorentz series expansion of this form. Here the positive terms I have written as a single term, and the negative powers I have written as a separate terms. That is the reason, because uh, the quantity b1 upon z minus z naught plus b2 upon z minus z naught squared, etc. till bn upon z minus z naught to the power n plus etc. is called the principal part of f at z naught. Okay, so based on the principal part only, we are going to classify the singularities into three categories, right? The first one is if the principal part of f at z naught contains at least one non-zero term, but the number is, that is the number of such terms is only finite, then there exists a positive integer m with m bigger than or equals 1 such that bm, which is non-zero, but your bm plus 1, bm plus 2 and all other quantities are 0. Okay, after that stage, after that m value, all your bm values are 0. So in this case, the principal part is or in this case the function takes the form f of c equals summation n runs from 0 to infinity an multiplied with c minus z naught to the power n plus b1 upon z minus z naught plus b2 upon z minus z naught squared till bm upon z minus z naught to the power m with the validity in this domain. Here your bm must not be equal to, okay, must not be equal to 0, right? In this case, or here the isolated singularity z naught is called a pole of order m. Okay, a pole of order 1 is called a simple pole, right? So now let us see some examples. So the first one is the given function is z squared minus 2z plus 3 upon z minus 2. So this may be written as z of z minus 2 plus 3 upon z minus 2, and this may be written as z plus 3 upon z minus 2, and you have to expand everything about 2. So we just add and subtract 2 to write things in this form. So clearly f of z has a simple pole at z equals 2, and residue of this function at this point is 3, right? And the validity of this expression is 0 less than absolute of z minus 2 smaller than infinity. Now we move to the next example. Your f of z is 1 upon z squared multiplied with 1 upon z. So here this may be written as 1 upon z squared multiplied with 1 upon 1 minus of minus z, so that it shall be written as 1 upon z squared multiplied with 1 minus z plus z squared minus z cube plus z to the power 4 minus z to the power 5 plus etc. And when you take things inside, you get 1 minus z plus z squared minus z cube plus etc. This f of z has a pole of order 2 at z equals 0, and residue of f of z at z equals 0 is minus 1, right? Here the validity is in this punctured disk. The next example is sine hyperbolic sine z upon z to the power 4, this may be written as 1 upon z to the power 4 z plus z cube upon 3 factorial plus z to the power 5 upon 5 factorial plus z to the power 7 upon 7 factorial plus etc. This is 1 upon z cube plus 1 upon z 3 factorial or 3 factorial z plus z upon 5 factorial plus z cube upon 7 factorial plus etc. Okay, this function, this f of z has a pole of order 3 at z equals 0 and the residue of the function at z equals 0 is 1 upon 6, that is 1 upon 3 factorial. Here the validity is in this punctured disk, right? Now the other two singularities, other two isolated singular points, that is the removable singularities and essential singularities, are to be discussed in the upcoming lecture. Thank you.